Hello everyone. Welcome to episode 11 in the op-amp tutorial series, Input Bias Currents, Input Offset Currents, and How to Measure Them Part 1. I split this topic into two parts because it was getting fairly long and there's a pretty natural split between the mathematical derivation of the effect on inverting and non-inverting amplifiers and the test circuit and demonstration. Today in Part 1, we will be introducing the concepts of input bias current and input offset current in op-amps, and exploring the implications of these currents on the inverting and non-inverting amplifier configurations. In Part 2, we will introduce a useful circuit for measuring the input offset and bias currents of an op-amp, and demonstrate that measurement on an LM324 in the lab. Thus far, we have assumed that the input currents into the op-amp are zero. In real op-amps, these currents are not zero, and for precision circuitry, as well as circuits amplifying sources with high impedance, we cannot generally use the ideal assumption that the input currents into the op-amp are negligible. These input currents are commonly referred to as bias currents. The range of input bias currents depends on the kind of transistors used in the op-amp's front end. For bipolar op-amps, the input currents are the largest, being in the nanoamp range on the low end, or even less in very special cases, with up to as high as 100 microamps on the high end. Higher speed bipolar op-amps tend to have very high input bias currents, on the order of a few microamps at least, so watch out for that if you're looking for a high-speed op-amp. Typically for most bipolar op-amps at around room temperature, their bias currents are in the range of tens to hundreds of nanoamps. JFET input op-amps are pretty low current, though there's a significant temperature dependence. Typically they stay in the mid to high picoamp ranges for most devices at room temperature. CMOS input op-amps have the lowest input current, and they have a similar temperature dependence to JFET input op-amps. Typically they tend to be in the 1 to 100 picoamp range. Given these numbers, you might be tempted to swear off bipolar op-amps categorically in favor of MOSFET and JFET op-amps due to their much lower input currents. However, each transistor type has many advantages and disadvantages, and input current is only one parameter in the overall design, and whether or not it matters more than another parameter is very dependent upon the design in question. When talking about the input currents into op-amps, we tend to treat them as currents rather than resistances. There are a few reasons for this. Firstly, in the case of op-amps with bipolar input stages, which generally have the highest input currents, an input current is more accurate than a resistance, as the biasing network is usually designed to try to keep the collector currents of each input transistor at fixed values. And since the currents into the op-amp inputs are the base currents of those input transistors, and base current is proportional to collector current, then the input currents are mostly independent of the input voltage. The second reason is that treating the input currents as currents rather than resistances significantly simplifies the analysis without losing much accuracy, especially if the input currents are small. The input currents for CMOS and JFET op-amps are a little more complicated. CMOS input stages are dominated by the reverse bias saturation currents of the ESD protection diodes, and the input currents for JFET input stages consist of both the ESD diode currents and the JFET's own gate source PN junction. However, although these appear to be current sources, there are still voltage dependencies determining how solidly reverse biased these structures are, leading to a dependence on voltage. So there is a resistive element, though it's highly nonlinear. So in the case of MOSFET and JFET input stages, even when the input current is a partially resistive effect, in these cases the currents are so low that the resulting equivalent resistance would be so large that it can be approximated as a current source without losing much accuracy. Finally, many variables such as common mode voltage, temperature, supply voltage span, and part-to-part variation affect the input bias current in frustratingly complex ways, which means that even if additional accuracy is obtained by modeling the inputs as resistances, that additional accuracy is lost due to other sources of error. Indeed, the dependence of input bias current on common mode input voltage is one of the reasons that the inverting amplifier configuration has a generally higher linearity. And so it is best to simply model bias current as a current source, and design your circuit and select your op-amp so that the input bias current does not have a significant impact on the output, even if it changes by a significant amount within the datasheet's specified range. If further accuracy is required, SPICE simulations and thorough testing of the physical chips can be done to further refine the analysis. Here we have the ideal op-amp again with its tenets listed below. Notice I haven't added the input offset voltage adjustment to the tenets from the previous video because, due to the principle of superposition for linear circuits, we are able to deal with the implications of each of these non-idealities separately and combine them together later. These two equations are the ones that we will change to be non-zero. We'll define them as IB plus and IB minus. Here again I show a simplified BJT input stage for an op-amp, and again while this is different from JFET and CMOS input stages, it still illustrates the concept sufficiently for any input stage type. Looking at this, you might think that the input currents are always positive, as current always flows into an NPN BJT base when it is in one of its forward operating modes. For this particular kind of stage, the currents are always positive. However, this is highly dependent upon the op-amp you are using. Many op-amps, especially rail-to-rail input op-amps, will have two complementary input stages, one with a pair of NPN transistors and one with a pair of PNP transistors, in parallel to permit extending the input range to both the positive and negative rails. They also help to cancel out the input currents to make them much smaller. Be sure to check the datasheet for whatever op-amp you are using to see the kind of currents you can expect, and if they have an equivalent circuit, inspect what kinds of transistors are drawing current from the inputs. In this kind of circuit, mismatches between the NPN set and the PNP set of transistors give rise to a non-zero bias current. But without loss of generality, let's go back to our single set of input transistors, since it's simpler. This input stage draws approximately equal currents into each of the BJTs. However, these currents are not identical due to mismatches between the transistors and biasing circuitry, just as we saw with the input offset voltage. This mismatch gives rise to a mismatch in the two input currents that is referred to as input offset current. Input offset current is defined as the difference between the two input currents, IB plus and IB minus. For bipolar op-amps, manufacturers try to make the two sides of the input stage well matched, and so the input offset current tends to be around an order of magnitude lower than the input bias current. The input offset current tends to cause more trouble than the input bias current because, as we'll see in a moment, if the input bias currents were exactly equal, we can make some modifications to our op-amp circuits to cancel out those currents completely. Datasheets tend to have values for both input bias current and input offset current. Since the input bias currents are assumed to be unequal, the formal definition of input bias current is generally considered to be the average input bias current, or IB plus IB minus divided by 2. Now that we have our definitions, let's take a look at how this affects the inverting and non-inverting amplifier circuits. Here we have our non-inverting amplifier. First we'll zero the input voltage, and in so doing recall that since the input is zeroed, the inverting amplifier circuit and non-inverting amplifier circuit are the same from the perspective of the input bias currents. So this is actually a case study for both the non-inverting and inverting amplifiers. Next, even though we're zeroing the input voltage, the input resistance is not zeroed. Even low resistance sources have some resistance. And now that the input current is non-zero, we need to pay more attention to the source resistance. So we add R3 here, encompassing all the resistance on the non-inverting input. And the first voltage to compute is VOP+, which is simply negative IB plus times R3 by Ohm's law. Using the ideal op-amp tenets that are still in effect, we recall that VOP minus is equal to VOP plus, so we now know VOP minus as well. Looking at the inverting input side of things, we note two more currents, I1 and I2. Since we know VOP minus, we have a straightforward expression for I2. Now using KCL, we write the equation for I1 in terms of I2 and IB minus, and now we have the expressions for I1 and the voltage of VOP minus. We can use them to construct an expression for V out. Now we just perform some substitutions from previous equations to get the expression for V out in terms of known parameters. Then perform some simplification steps, and we get an expression for V out in terms of the two bias currents and the resistor values. Now this does show the output voltage when looking at the two bias currents individually, and sometimes this is a useful equation, especially if you have measured values for each bias current individually. But as I mentioned previously, datasheets give values for bias current and offset current. So let's convert this equation from IB plus and IB minus to I bias and I offset. Here we have our definitions for I bias and I offset. From this, we can construct two simple expressions for IB plus and IB minus in terms of I bias and I offset. And now we substitute these new expressions in for IB plus and IB minus in our expression for Vout. This next bit is just some more algebraic rearranging, which I show for completeness. When it comes to the equation-heavy portions of these videos, it's not that important to pay attention to each algebraic step. It's more important to understand the beginning, the end, and the approximate path that was taken to get there. And here we have a nice equation with the I bias and I offset split out with separate coefficients. Now let's note that in both coefficients, the non-inverting amplifier gain value features prominently, and unsurprisingly, the higher the gain, the more of an effect these input currents have on the outputs. Now, first I should warn against the impulse to cancel out this entire equation by carefully setting all the resistors based on I bias and I offset. We don't actually know I bias or I offset. We only know the range that they could be, and their values change based on the op-amp's input voltage as well as its temperature in complex ways. For example, here is a plot of typical input bias current versus common mode input voltage for an ADA4096-2 chip from its datasheet, which happens to have a pretty thorough datasheet, and we can see that there are 5 distinct regions, each having a different slope that is different for different temperatures. It's important to note that I chose this op-amp because it has a lot of information in its datasheet, and most rail-to-rail input bipolar op-amps probably have similar or worse characteristics on their input bias currents, even if they don't have these characteristics documented in their datasheets. So just because this looks weird and nonlinear doesn't mean it's uncommon, and some op-amps may have bad behavior that is not well known because it's not documented in their datasheets. Manufacturers are not required to put this level of detail in their datasheets, and so datasheets tend to be a balancing act between too little information and too much information. The ADA 4096 is a part with a space-qualified version, and so its customers tend to be companies that need more information, and will only select parts with a high level of detail in their datasheets. That is likely why this part's datasheet has so much more data in it than is usual. So the only real way to determine the input bias current and input offset current for a given op-amp is intense testing over all applicable operating conditions for each unit used, typically not an economical or realistic option. So back to the equation. We see that for I offset, there isn't a way to zero out that coefficient. You can only minimize it by minimizing R1, R3, and the gain. However, for I bias, there is a resistance optimization that allows you to zero out the effect of I bias completely regardless of its value. Let's derive that optimization now. So to start with, we separate terms by their sign, so R1 is on one side, and the R3 times the non-inverting gain is on the other. At this point, we think about the order in which an op-amp circuit is designed. The process starts with designing the gain first, then the resistor values afterwards to optimize for power and other parameters, like input bias, offset, current, and noise. It is usually easiest to design R3 last, as it has little to no effect on the remaining circuit, barring circuits with very high input impedance. So we should find the optimal R3 given the values for R1 and R2, which are assumed to be already designed. So, dividing both sides by the non-inverting gain, we have this expression, which, with a little rearranging, results in an expression for the parallel combination of R1 and R2. So for parts with large input bias currents and low input offset currents, setting R3 to the parallel combination of R1 and R2 will cancel out the input bias current, and you can focus mainly on designing the resistances to be low enough so that the input offset current doesn't cause a problem. It is important to note at this point that in many cases, especially with parts with low input bias currents, that oftentimes increasing R3 so you can cancel out the bias current will lead to more problems than it solves. Higher resistances lead to higher voltage noise and increase the effects of op-amp current noise. We will get into the details of these drawbacks in future episodes as they deal with concepts we have not yet introduced. There are also some cases in which the input currents are not designed to be well matched, usually in op-amps with already very low bias currents, and so trying to cancel out the bias currents by increasing R3 will actually make things worse since you'll just increase the coefficient on the offset current. In these cases, it's just best to minimize resistances as much as is reasonable, and design such that the input bias currents don't affect the output voltage significantly. Check the datasheet values for input bias and offset current to see how far apart they are and if there are any notes in the datasheet about whether or not bias cancellation is advised. As a final note, the effect of input bias currents on op-amps is a purely DC effect, and as such, it only really affects the circuit output at the DC level. For AC effects, the input capacitance of the op-amp dominates the input currents. This means two things. When feeding a purely AC signal to an op-amp circuit, like with an AC coupling capacitor or a transformer, you need to make sure there's a DC path for the input bias current to go through and return to the op-amp power supply rails. Usually a large value resistor to ground is sufficient. Otherwise, the current will effectively flow through the insulating materials that separate the input from the op-amp's power supply rails to complete the circuit, and the input will float up or down until it hits its maximum or minimum range because that insulating material has an extremely large resistance. If the AC coupling capacitor is particularly large and the input currents are very small, it can take minutes or longer for the bias current to charge up the AC coupling capacitor enough for this to happen, which can make things very confusing when the circuit suddenly stops working after being powered for a while. Secondly, if you only care about the AC content of a given op-amp circuit's output, then you can mostly ignore the input bias currents, except insofar as they make the output offset large enough to get too close to the rails. Note, however, that increasing an op-amp circuit's resistor values too much can cause other problems like increasing noise and making the system unstable, so keep that in mind when you're increasing the resistances in this situation to reduce power. That concludes part 1 of this topic. In this episode, we introduced the non-ideal op-amp concepts of input bias current and input offset current, discussed how they affect the non-inverting and inverting amplifier configurations, and showed how to cancel out the bias current so that only the offset current affects the output. In part 2, we will be introducing a good circuit for measuring input bias and offset currents, and demonstrating that circuit on an LM324 in the lab. Thank you for watching the video. If you enjoyed it, please like, share, and subscribe. If you have a question or comment, please leave a comment. See you next time.